Good afternoon and welcome everyone to today's webinar on getting closer to urban and BVLOS operations, reflections from recent flight testing at Cardiff and Heathrow. We're delighted to welcome Chris Daniels, who is Chief Commercial Officer at Flight, to today's session, and he will tell us everything that's been going on there. Chris is a strategic advisor on commercializing startups and scale-ups, focusing on the aerospace and defence sectors alongside big data tech and machine learning. And we're delighted also that he has joined us as an ARPAS-UK director. But today he is here in his Flight capacity to share some of the knowledge that they have been gleaning. Carl Sequeira, who is their I've just flicked away from the wrong page.
Head of Engineering.
Is a chartered engineer with the Institution of Mechanical Engineering, and he's a multidisciplinary engineer with commercial and academic research expertise spanning aerodynamics, modelling and simulation, design and testing, and device performance. He will be joining us shortly too. We're delighted you're both here, and I'm just going to ask you to kick off the section, and off we go.
Great. So hopefully you should be able to see my screen. Just confirmation from Eleanor.
Yes, we can, no problem. Thank you.
So what we're going to do on this is split it into two. I'm going to talk a little bit about Flight and our technology and sort of how we've got to doing these various flight tests and wind measurement tests at Cardiff and at Heathrow Airport. It is an offshoot of something else we're doing, and I'll explain that, and then I'll hand over to Carl, who has been running the flight tests and is the sort of real engineering guru behind all of this. So Flight, who are we? We're a 7-year-old company. We basically do software for drones. We've done a number of DASA Defence and Security Accelerator contracts. We're now on contract with both the Ministry of Defence and the US Department of Defence. And on the commercial side, we've been involved with the UKRI Future Flight Challenge in all phases, and we've been involved in a couple of projects on each. And the wind measurement is very much one of the future flight projects, and we'll talk about that in a bit more detail. And we've been on various accelerators. So last year we were on the Boeing Aerospace Accelerated program, which was excellent. We've been part of the Oxford University Side Business School Creative Destruction Lab, which is also very good. And we are currently on the Connected Places Catapult Future of Air Mobility Accelerator, which started last year and runs through till end of next week. And that's what's allowed us to do some of the testing at Heathrow. So it's all sort of come together on various trials and projects that are mainly UK government funded. And in terms of, I think a lot of people are always interested in a company's history. So we were founded by Kelvin Hamilton, whose background was at a subsea autonomous company called Seabite, and that successfully sold back in 2013, and he started Flight. So, and we kind of started our machine learning development, machine learning digital twins development in about 2018, and then came through into 2019 to start doing more flight testing. We were still pre-revenue at that stage, and our first revenue came from DASA, from the Defence and Security Accelerator, in September 2020. And really since then, we've accelerated off of that platform. So we've done outdoor flight testing. We're at a place called Westcott Venture Park, which is just northeast of Oxford, and we do our flight testing here within the business park. We've had follow-up DASA contracts. We then did August 2021, did our first wind measurement trials at Cardiff Airport, and got what we call our first grown-up contract in September 2021. And then we've sort of moved on from there and kind of accelerating away, including United States Department of Defense funding more recently. So that's the sort of overview with some of the highlights of where we come from. And who are we? I've mentioned Kelvin. He's PhD in autonomous systems. He's our CEO and an electronics engineer by background. Conrad is our artificial intelligence guru, and he really is the brains behind the software. I tend to do the trade shows and the talking. And then Carl, who you meet later, is the real kind of aeronautics engineering expert. And we're complemented by another 12 people that we've brought on and trained up. And we'll be 20 people by the summer. So we're growing quite a lot at the moment. We've had various customers, so Boeing, fire service, police, army, etc., all kind of generally validated our technology. And we've got a sort of very nice quotation from the MOD saying that they kind of like what we're doing. So what do we do? So what we do is we take inertial measurement unit, so the sort of standard thing you'll have in a mobile phone, and pretty much every drone has got them, little tiny MEMS sensors. And offline, we train that IMU in relation to the drone that it's in. So we model the whole drone, the flight characteristics, etc. And we use machine learning to throw every single conceivable scenario at it, every wind configuration, every configuration of its control surface, of its thrust, of the forces on the drone. And we will understand exactly how the drone works. And that allows us, when we put that software back in the drone, it allows us to predict exactly where the drone is flying. So eventually, we've enhanced the IMU to make it a decent inertial navigation system. And so these are actual flight test results that we've got here. So if you have an IMU on its own, you get the sort of dark blue parabola type line, and the error, the navigation error, runs away. Whereas with our technique, with the offline machine learning, we cap the rate at a linear level and we reduce it massively. So if we, and this was really for demo purposes, we didn't fly from Newark to Central Park in Manhattan, but for illustrative purposes, if you have a standard inertial measurement unit on a drone, it will get sort of over a 5-minute flight, it will not know where it is to the tune of about 15 kilometers. It really loses its accuracy really rapidly. With our technique, we're going to get within a couple of 100 meters of where it's meant to be. So that means we'll be able to Central Park at that stage. And this is off the basic, cheapest IMU. If we use better IMUs, we'll get sort of proportionally better results. And in terms of, so from a military perspective, being able to have a system that allows you to fly without recourse to GPS or have a backup to GPS is really useful. But if we do have GPS on it, the only force that we don't know during flight is the wind, and that's how we work out what the wind is in flight, and that's what we're really going to talk about for the rest of this presentation. And how we've done this, so we started off with a tiny Nano Drone glider that we developed ourselves, which is at the bottom corner of this slide. We've moved on to a hobbyist drone, and we're moving through kind of more exotic and more representative drones. So and the solution, because it's software based, is fairly simple. It's affordable once we've actually done the modeling work. There's sort of minimal additional cost, and it's very low compute power and any sort of consumption of electrical power, so it's less than 1 watt. So you've got a sort of self-enclosed system there. And this is the actual Nano Drone that we're using, and we have been using to measure wind. So it's got 2 elevons at the back, 2 control surfaces. They work autonomously, so we use some sort of device to give it thrust, we actually use a converted sort of tree line thrower pneumatic launcher, so the thing that shoots a rope up to get over a large tree. And we've just adapted that to launch our drone. It weighs 90 grams, fits in the palm of the hand, and it's got a really high frequency update rate. So, and it doesn't use pitot probes, it doesn't use GPS, it just measures exactly how we're flying as we go along. So, wind measurement, we validate, we've been validating CFD wind maps on a project that was phase 2 of Future Flight called Safe Zone. We, our partner company Xenotech, developed really good high fidelity computational fluid dynamic wind maps, but they needed another source of ground truth to validate those maps. That's what we provided at Cardiff. And then we've been doing some testing more recently at Heathrow, which allow us to validate and understand a little bit more what's going on in a sort of more complex environment with more hangars. So I'm now going to pass over to Carl, who's going to talk you through the actual results that we've been doing and what we were doing at both Cardiff and at Heathrow. Carl, over to you.
Hiya, just walked into this, so hopefully I won't repeat anything that Chris has said or not said. Oh, stuff on that board. So the Safe Zone project, it began with a simple premise. Drones tend to struggle in very gusty environments. The smaller the drone, the more susceptible it is to length scales that offer similar magnitude to it, of course, and there are plenty of those kind of flow conditions that you might experience in a built-up site, so urban environments. And that's a challenge because everything we talk about in the drone industry today, civil drone industry, is really centered on urban air mobility, flying in cities, small drones flying all of that. So responding to those environments correctly and understanding how they would respond to that is a key safety concern, a key regulatory concern. So a high fidelity understanding of that wind as a map is considered critical. It'll help us understand operational restrictions. It will also help us design safer, more responsive drones if we actually understand the right conditions they're flying in. And that's the key starting point for what we're doing here. Now, why is this difficult today? Well, measuring wind is an interesting challenge. So if you look at Met Office models, they're limited in resolution. And a large part of that limited resolution is because we just don't measure enough of it. And if we were to try and go and measure it, if we want very accurate, detailed profiles, we've got to use LiDAR, which is expensive, difficult to sort of put out anywhere we want. And we've got sort of interference issues as well in complex environments. If we go back to the standard way we verify Met models, or any wind-based models really, we get back to the standard anemometers or little anemometers that are put up in balloons, but really static anemometers that we put in a position somewhere. And they are inherently single site, limited to that restriction, and a single data point is just not sufficient to accurately verify a model against. You've got potential expenses of putting on a new anemometer in different locations, restrictions around that, and of course you can't get, with any of these static measurement systems, you can't get very high frequency data that allows you to truly capture the unsteady complex flows that you might have in an urban environment. And that's really where the wasn't expecting this slide, but that really is where this project began. And it is centered on Xenotech's ability to measure or to model the wind, but really our capability is Flare Bright with our Snapshot to develop a high resolution wind measurement capability that can verify these models. We've developed a patent pending machine learning inspired wind sensor capability. And the beauty of it is that along its flight path, gives us essentially a 3D real-time wind measurement result without using things like pitot probes. So it's very highly spatially resolved. And we've tested this, as Chris mentioned, at Cardiff Airport against static anemometers and used it to then verify the CFD data that Xenotech has developed. And we've now more recently tested this at Heathrow. So specifically, the Cardiff Airport project was centered on a UKRI Future Flight Phase 2 project. I'm delighted to say we're actually in a Phase 3 version of that now, where we're taking this capability beyond. I'll talk to you about that perhaps briefly later. The overall ambition of the Phase 2 project was to demonstrate a route to wind data as a service for unmanned air traffic management systems. So that service is a service provided by Xenotech, and we were basically providing that verification tool set. We used Cardiff Airport as an operational test case because although we're talking about this as a complex flow environment in an urban environment, in practice, regulations would not allow us to actually fly in a fairly congested environment easily. So instead, we used Cardiff Airport. They were very kind enough to allow us to fly near the British Airways hangar. And it provides a perfect representative case for us to demonstrate how Flyby's Snapshot drone could be used to actually measure 3D unsteady data. And this was then used to validate the CFD models developed by Xenotech. Now, this is a video, just for context here. So Chris would have given you a little mention of Snapshot as a vehicle. So the way we flew it at Cardiff and the way we fly that vehicle is we fly it in a vertical path upwards. So it effectively measures your wind shear profile before it then loops back to come back and fly down to a fixed target nearby. This is a simulation. Oh, and I'm not sure if that's working. I'm not sure what you're seeing. Eleanor, you can protest if you're not seeing a live video.
Hi, Carl. We're not seeing a video actually at the moment. I'm not sure whether Chris input one. When we spoke on Thursday, he wasn't going to. Right.
Okay. Let me just get back to the screen. Just if you tell me which of your tabs it is. I'll just skip the video. That's fine. Hopefully my words were good enough. It is so yeah. So just picture this: something flying straight up like an arrow, all the way fired up to an apogee of about 60 meters before it does a little loop and then flies back like a boomerang towards the, not directly towards the user because we deliberately target it about 10 meters away from us for flight safety reasons. I'm sorry you missed out on that video, but we'll just crack on. This is the, you can still see the presentation, is that correct, Eleanor?
Yes.
Perfect, lovely. So we're looking at a top-down view, Google Maps, yeah, of the British Airways maintenance hangar at Cardiff Airport. And we've highlighted two sites that we tested at. Both of them are airside, so we had to go through the entire process with Cardiff Airport to make sure we were all fully engaged, had all the appropriate positions in place, permissions in place, and worked very closely with ATC. The first site, Site 1, is located slightly further away from the runway and gave us a little more freedom to do what we wanted to. And then Site 2 is very close, well, it's within the line of control. But it gave us the opportunity to fly two sites depending on the direction of the wind, so that we can maximize the type of conditions we could measure where the wind was going over the building. This is a Google image that sort of fixed in point in time. So the aeroplanes were not where they are in this picture when we were actually flying. That said, similar ones a little further down the hangar, so near the engine test bed bay there, actually did represent reality, and you'll see why I reference this later. think I've got another video here that's not going to work. Let's see if this one works. But this is us actually testing at Cardiff, but I don't think it's going to work, I'm afraid. So what you can see is a still of us testing at Cardiff. And it's probably useful to point out here, we had our own little static anemometer positioned fairly nearby, and a windsock to help us judge the wind conditions locally to where we were launching. I'll move on from this. Apologies. I'm sure the videos, you would have all appreciated the videos, but that's what it is. Over here, we've got a closer look at the launch sites. So when we did the test at site 1, we only had that nearby anemometer, the thing I referenced now is the 4-meter anemometer near us. With site 2, by the time we got around to testing at site 2, we had also installed a secondary xenotech anemometer to the fence line of the airport, and that provided a secondary point of verification. Now, it's important to note, of course, these are not exactly where we launched, and therefore they will be measuring slightly different flow conditions in a fairly complicated flow environment than the point that we're flying. But it still provides a very useful point of verification for the measurement system. So at site 1, we've got 2 little arrows here, 2 green arrows that show you some of the direction of the mean wind conditions on the day that we were testing. And on day 1, we effectively had a flow that goes straight over the building. So we'd expect to measure a fairly vertical, disturbed flow because we're quite in the boundary layer there. Day 2, less of an issue because we're actually the free stream wind conditions were being measured, not over the building. But there's a deliberate photograph here for this reason. As you can see, there were aircraft in the direction the wind was coming from. And you will see in the results I show you that we can actually see some of the subtleties from the influence of those aircraft on the flow conditions we measured. So on day 1, and these are just example results, just as a showcase the kind of 3D conditions we're measuring here. We've got a plot here of the magnitude of the wind, the length of the disturbance of the magnitude of the wind. The colors are the bearing of the wind, but you can actually see that in 3D here in terms of how the flow is rotating. And what you've got there is effectively a complex vortex, sort of moving very disturbed all the way up through the height of the flow that's been measured. And that was rather remarkable because we could then actually check this out in the CFD results of the same situation. On day 2, when we're going over this largely free stream flow, no real disturbance, we've got what is a largely uniform flow profile, with the exception of the area around the 10 to 15 meter mark, where you can see that there was actually some flow curvature, hence the bearing is different, the color is different, and that actually corresponds roughly to the tailplane of that aircraft and the influence we were seeing there. So it's really nice because even from very simple basic analyses, just plotting the results, you can start to see some of the flow features that you certainly wouldn't capture with a single point in space static anemometer. This is an example of the same kind of thing on when we're measuring at site 2. You've got prevailing wind is an easterly coming across the building and across the engine test bed there. And you've got a very disturbed flow condition here. And once again, don't have the results right here, but it matched the CFD very well. So we're going to come to some of that verification here. And the way we've verified the measurements itself, the only really easy way of doing that was against fixed anemometers. Because let's make the assumption as a starting point that we don't trust the CFD. So let's treat the anemometers as our ground truth. And we had 3 anemometer sets available to us. We had what was the Skylink Airport anemometer, which was an average data set averaged over 15 minutes in a free stream condition. So far away, up out of the noise, where disturbances such as the disturbances that you see from the buildings would occur. So it corresponds to what I've marked here as an arrow, the free stream conditions. Oops, that's not going back. Sorry. So that's sort of that free stream state. We've got the 4-meter anemometer that was about 10 meters from our launch site that was pointed out to you in pictures. And we had the Xenotech anemometer for site 2 that provided a similar thing. So to compare, we've looked at the average data conditions, heights above 30 meters, because that was roughly the building height, to say that's the free stream conditions, or prevailing free stream condition that we measured. And we've tried to compare this against all 3 data sets. And of course, as I've said here, it's not an exact means of comparison, because not all of them have the same sort of frequency of response. Not all these results are, well, the time averaged over 15 meters at Stockholm Airport anemometer. Then all the static anemometers are not in the same location. As you can see from the profiles I've shown you as examples, the flow is very disturbed in those environments, as you'd expect from sitting in the wake of a building. But despite this, we can see that there was a very good free stream match between the snapshot averages, so the red dots, and the skylinks. We tried to launch in conditions where, local to the ground, we were in fairly low winds, just to try and ensure safety in terms of the test environment. So it might have felt lower, and this is why the local anemometer, the 4-meter anemometer, actually measures a bit of a lull. The local anemometer is very useful here, even though it doesn't necessarily track exactly with the average conditions. It's useful because the range of the measurement there, the measurement noise in that high frequency 4-meter anemometer, gives you an idea of the effective error bars that any of these average results might have further around the place. So that's valuable there. You can see a similar thing if you look at the time averaged attempt of comparing the Skylink versus snapshot results for the bearing results. I don't think I've shown you yet. Similar results here shown for site 2. And as you can see, so overall, a reasonably good picture of reality. Oh, I do have the bearing stuff here. So this is exactly the same perspective, but instead of the wind magnitude, we're looking at the bearing predictions. Once again, the local anemometer, the 4-meter anemometer, even the Xenotech, has a bit of an offset compared to the free stream results that we've sort of time average from Snapshot or from the Skylink results itself. And that's what you'd expect. It's localized at a given site. It's being influenced by the flow conditions right there. So it's never going to capture that free stream condition very well. But that's what you can capture as you go through the loop with the Snapshot. So from a free stream condition, we were satisfied that Snapshot gives us a really powerful way of measuring the results and to a reasonable accuracy. What about the complex flow? Well, the complex flow conditions we can't actually measure or verify in any way from those static points. And we've just shown why. So qualitatively, they looked believable. Quantitatively, are they believable? It's hard to say explicitly without actually starting to use the CFD. So Xenotech produced some exceptional CFD results against those free stream wind conditions that we measured and that the Skylink system measured on the flight days we were testing. And what we found qualitatively was the flow structures were very similar to the wind estimates that we produced. The exact result starts to become a slightly more difficult to compare, result to compare with, because of course, you've got to get your instant of time absolutely right. So how do you do this appropriately? What metric can you use to compare the data with to a level of accuracy that you would sufficiently deem accurate? And at what point do you start to become a circular argument where you say, oh, actually, you're using the CFD to verify measurement system, and the measurement system is being used to verify the CFD. So that starts to become a bit of a philosophical argument and discussion. But what we can say is that we have demonstrated that we can do some very accurate 3D unsteady wind sensing, done at an airport within tight operational conditions. And we've also made an attempt, and this is the stuff of an ICAS paper, if you want to go look at it, at trying to qualify just how we can close this validation loop. I'd be delighted to hear any feedback you have once you've read this paper. So the value we got from that project was we saw that, well, we firmly believe that wind sensing is critical to improving flight safety. And we saw that Snapshot as a device can provide very precise data for specific operating conditions. Now, can you go beyond that? Can you start to use this ML-based system on any aircraft? And can that then start to actually feed back to a wider air traffic control system, which allows real-time situation monitoring, helping provide safer onboard warning systems, improved operations, improved forecasting? That is some of the discussion and philosophical argument we're going through now as part of Safe Zone Phase 3. So watch the space. Hopefully we'll get some answers to you, well, this time next year. At this point, it's worth talking about Heathrow. So if we take this wind measurement capability from the context of a specific flight ops scenario, one of the most ideal operational use cases would be to actually measure the wind conditions at possible sites that you'd like to test a vertiport, so that you have a realistic understanding of the flight conditions that will set your operating limits for any vehicles operating on that site. That was the purpose of the Heathrow Airport trial, to gather wind data at exemplar test sites to sort of showcase this idea of how you can use accurate wind data for the purposes of siting vertiports. Now, the challenge, of course, when you're working with an airport, the size and complexity of Heathrow, is making sure you get the permissions correct, and making sure you fit in with the wider operational activities at the airport. So this particular exercise, and I'm not going to show you any results because it's literally hot off the press. We've just completed this last week under the auspices of the Future Air Mobility program run by the Connected Places Catapult. But it's been a phenomenal exercise for us in achieving and understanding how we operate at a complexly regulated environment like Heathrow, and how we fit in with those operational activities, which in our case was actually operating by night, which is not something we've done before. So just for some fun, we'll close this with a few fun pictures of the team at Heathrow Airport at night. Airside, this is near the southern runway. That's one of our team members set up, ready to fly with his software. This is Snapshot on the launcher, ready to go. And this is about to launch. And the team looking very pleased with themselves after they had managed to get the flights we wanted and the results we wanted. So very successful test. We're now analyzing the results to see about accuracy and to see how we can start to story this in the context of a sighting of vertiports example. So open questions, and I guess we'll open the floor to Chris and myself here. Is, of course, where do you think, as a wider community, could our wind measurement capability be useful? Do you see any aspects of this that might be more helpful than others? And of course, and this is slightly controversial depending on who you ask, is how comfortable do you think people would be doing live wind testing using a system like this in the wake turbulence generated by aircraft, live aircraft as the takeoff? What is your sense of commercial viability? These are all questions we're grappling with and understanding as we try to make a case for wind measurement, but would be more than open and interested in your viewpoints. Thank you.
Typically with advanced air mobility and EV cell air taxis as well. It's quite interesting about how the wake turbulence and the wind impact, particularly in urban vertiports, is going to affect everything. So that's us. Eleanor, back to you.
Thank you very much, Chris and Carl. That was absolutely fascinating. Thank you very much. I'm personally not technical, but I was gripped by that. Absolutely fascinating. Thank you. So I'm going to open up the Q&A side of things, and please do ask questions via the Q&A section, and we will start an interesting conversation, I hope. Thank you very much, though, indeed, Chris and Kyle. That was great. Really interesting. And as you say, it's going to open up some interesting ideas for the vertiport side of things, as to how vehicles will be able to operate within that sphere. Right. Now, so far, nobody is coming forward with questions, so I'm going to assume that everyone knows everything. Please do feel free to ask questions. That is what we're here for, to help understand some of these points, that to those who don't work with Flare-Bright, so that we can understand these further.
Or you're just overawed and rather impressed, and we'll take that too.
We have a question through, which is, what is your next step in gaining funding?
So that's a very good question. I think it's an equivalent question for every smallish business in this sector. We've taken, I think there's sort of broadly two routes you take. You either do a big equity raise and a series of equity raises in order to go down the civil commercial route, or you go down a sort of similar process in a defence route. The defence route tends to fund R&D in a lot more meaning. Once you've got a technology that's liked. So we did one seed funding round sort of during 2020, and that's all we've ever done, and that at the moment is all we intend to do, because all our funding is now coming from defence, in effect R&D contracts, and we're moving into kind of proper commercial contracts. So the next funding is the next commercial defence contract. We're sort of watching the space of what's happening in the commercial drone world, particularly around BVLOS, particularly around urban operations. Our view is it's not mature enough yet for us to achieve sales in that process. It may be that we do an equity raise specifically for that if we think it's sort of BVLOS or advanced air mobility is getting very close to fruition, but we just don't see that. And it broadly would take us 6 months to put an equity offering together, and we don't see that happening in the next 6 months. So this is one of the reasons why we've focused a bit more on defence. So hopefully that answers your question. It's a complex moving feast, as you can imagine, at all periods of time.
It is indeed. Thank you. That's really useful. Please do ask questions. Bring them on. We have knowledgeable people here who are ready and waiting. So again, from the same source, have you looked at the US DoD or other defence agencies like Towers and SDF in the UAE?
Yes, it's a short answer. So primarily we've been MOD funded, but we do have US DoD funding. The challenge with the US DoD, as anybody in defence will know, is ITAR. So we're proceeding with caution, but at the same time, the US DoD's budget is more than every other kind of friendly nation's budget put together in terms of defence. So you'd always look at those as a prime candidate. We haven't really spent much time looking beyond UK and US for that reason. And so Tawazan, interesting, is now a partner on the Boeing Aerospace Accelerated program. Through that, even though we did it last year, we're our alumni and we're quite involved with them. So for example, Boeing have invited, I think, almost 20 of the cohort programs of all 4 cohorts that they've sponsored on the accelerated program to showcase at the Paris Air Show under a sort of Boeing banner. And so through that, we sort of got these ongoing relationships. So whether we do look at, you know, EU countries, other NATO countries, Middle East, I think that will all happen in due course. I think what most people do is look at your home nation as a reference case and the US DoD as a second reference case. And once you've got both of those, the sort of process kicks in nicely. And we're still doing proof of concept work with both of those organizations. So once we've kind of done, you know, more program of record stuff, which will be soon within the next 12 months or so, then I think we'll be in a better position to look at other export markets.
That's great, thank you. Please keep them coming through. Keep the questions coming. What are your plans around BVLOS?
Wow. What's everyone's plans around BVLOS, I think, is the bigger question. I'm probably going to defer to Carl. I'll sort of give us an initial answer. So our GPS-free technology, we feel, is a key enabler to BVLOS. So BVLOS, you know, every system that is used in BVLOS has flakiness attached to it. So GPS, particularly in urban environments with sort of backs of buildings, can be flaky. Visual nav systems can be flaky. Comms links can fail. And we've got a sort of, you know, a final source of truth that will always work and will always be available. You know, as I said, it's got a sort of linear error rate, so you can't rely on it for hours worth of flight. At some point, the error rate grows too much. But as a part of a navigation stack that will always work, that's where we see it. I think getting in any regulatory environment, getting regulatory approval for all of this and for understanding, you know, what is going on and what works and what's the reliability factors of all of this, there's still quite a lot of work to do. So where we want to do BVLOS is be a sort of final grand truth that is recognized by the regulators. I think that's going to take, you know, a bit of time for that to be understood, and a bit of time meaning kind of years, not months. But Carl, I don't know if there's anything about it.
No, I think Chris captures that really well in terms of our core GPS free capability. I think it's a very open-ended question. What exactly are people searching in BVLOS? And it really depends on the use cases and how the systems are intended to be used. But the heart of it and the heart of where this industry is going to go will be determined by how easy it is to regulate the system. And one of the things we are exploring as an idea is underpinning our capabilities is a means of using machine learning to rapidly test and evaluate capabilities of a system. And one of the things we'd like to understand is whether that rapid test and evaluation capability is a means of then achieving the levels of certainty and assurance that can help satisfy regulatory authorities without necessarily requiring extensive tests for all of these smaller drone systems at least. And if so, could we then be a pathway to achieving BVLOS faster? That is in addition to and beyond providing specific capabilities like the wind measurement of the GPS free that we believe will help in certain ways to achieve the safer conditions that will allow a vehicle to fly.
Great, thank you. So we have one here. In your opinion, what are the main regulatory hurdles?
No comment. I'm not going to get in trouble with that one.
Carl, hi. What the this will link into the next question. You know so I think there's the regulator hurdles for what we're doing, and we'll cover that in a second. You know, what are the key regulatory hurdles? I think as we go through different environments, so we're doing a bit of work, sort of concept work with National Police Air Service about how they're operating, although how they're planning to operate drones in an urban environment. I think, you know, there are many solutions to achieving regulatory approval, and people have in sparsely populated areas and areas where, you know, there's sort of more knowns. I think as soon as you get into kind of urban areas with different amounts of flakiness, funny wind canyons, all this sort of stuff, there's still a lot of unknowns. And I think there's a lot of regulatory hurdles all around that. And it's not just one thing. It's not just, you know, how robust is your GPS? And it's not, you know, how well are the winds understood? It's, you know, what is the conspicuity and what system are you going to use for air traffic control or for unmanned traffic? How's that going to integrate with anything else going? You know, they're all sort of well-known problems, but I don't think there's one of them. I think there's 20. And then there's, interesting enough, so I was at there's a Future Flight conference a couple of weeks ago, and that was all about public acceptance. And there's still a lot of kind of genuine question marks about public acceptance. And broadly, all the surveys seem to say if it's in rural areas, people are really happy that that's a good use of drone delivery or urban air taxi. Air taxi. It's in an urban area, generally don't really see that there's a good use case, because it's basically going to be rich people shaving 50% off their time of travel, or shaving, you know, another few hours off their Amazon delivery. Well, from a public acceptance perspective, that's not going to work. And actually, I think that's a key aspect. The public acceptance needs to be part of this, not just a regulatory acceptance. But it's Carl, in our normal drinking establishment, which you know, I will chat to you for that. And then
that's very interesting. What sort of CAA approval did you end up needing for these flights?
For the Snapshot, really nothing, because we fly everything in open category restrictions. So we sort of chatted them through with the CAA sandbox, who were more than happy that everything we were doing does comply with open category restrictions. And then really the permissions and approvals that we needed were always based on the airports that we were flying at. So at Cardiff Airport, they required us to file a non-standard flight application. They'd already effectively discussed this well in advance, but we had to do that as a formality. So we went through the process, we explained to them what we were doing, then we formalised that with a non-standard flight application, and that was it. With Heathrow, they had their own series of processes. Interestingly enough, they didn't need an NSF, which is fine. They all have their own processes, procedures. But once again, at the heart of it is very much an R&D exercise, and the heart of it is making sure people understand what you're doing and that they're comfortable with what you're doing. And that was, of course, getting any of the permissions in place.
And actually, the challenge with Heathrow is actually achieving the required insurance levels, the sort of public liability insurance, because, you know, they're used to sort of fairly sophisticated aircraft coming in and out, and just the amount of cover that they would expect you to have is way in excess of what a tiny, you know, we would ever expect with a 90-gram drone could, you know, you can't conceive of us ever doing the amount of damage that they want the insurance for, but that's their process. But we sort of, you know, managed to agree something with on that.
Okay, that's great. Yes. So another question that's come through: have you looked at small coastal/island airports that we expect the EU to endorse for BVLOS cargo drones in 2025?
Yes, but not in as much detail as we should have. So, I mean, I've done sort of bits and pieces of work, and I won't go into them with specific either airports or operators looking at what we can do, but it's something, and Mark, it'd be good for you to drop us a note of what you've got in mind, because if there's something that you think we can work with on that, would be really interested.
That's great. Thank you very much. Are there any final questions as we come up to the last 5 minutes of our allocated time here? Oh, yes, we do. Do you see this measurement system being of use in offshore wind, e.g. pre-consent site assessment?
Shall I start with that? So we did look at this, and what's interesting is most sort of wind, whether onshore or offshore, tends to use LiDAR measurements, and it is flaky, and it, you know, oftentimes there'll be various weather conditions it doesn't work in very well, and, you know, there's sort of particular, it's when it's foggy, but what they tend to do is just extrapolate the data between, you know, the days it does work and the days it doesn't work. And given, you know, it's they're sort of normally putting wind measurement in place for a year or 2 years before they ever get approval, it's the sort of current solution is good enough. It's not perfect, it's good enough, and we're kind of like, oh, surely we could fit in, get better data on the days that your LiDARs aren't functioning properly. It comes down to commercial reality. How much of a commercial problem is it? And I think my interim conclusion, it's not my final conclusion, is it's not commercially a big enough problem just yet. It may well be in the future, but that's kind of where we got to. I don't know, Carl, if you want to add.
No, that's absolutely spot on. That said, there are still wind farm related operators who are interested in that sort of data, that sort of level of fidelity of data, because it helps influence the tiny optimizations, locations, and power generation, etc. As part of our current SafeSwim project, we may, and I emphasize the word may, we may be looking at doing a exemplar demonstration exercise with a possible wind farm off that hole.
Well, keep us posted if that does happen. That sounds, it certainly sounds a very useful way of measuring the wind there. Well, thank you very much. That seems to be the last question for the time being. Please, oh no, there is one more. You're being swift on the uptake now. Very interesting presentation. Great that Cranfield, the university, we have the opportunity to engage with Flarebright on many things. So I think that's more a thank you than a question. That's great. I'm glad you've enjoyed it. That's absolutely what we're here for. And we are delighted that Flarebright were able to join us today in the form of Chris and Carl. And I hope that you will share the information as well that we'll email through to you later on today or early tomorrow with wider colleagues or those who show an interest in this. Thank you very much, Chris. Thank you, Carl. Fascinating discussion, and certainly it's fed some thoughts into my brain too, to sort of take away and have a sort of further think about. Thank you very much indeed. Thank you indeed also to those who have given up their time to come and attend this too. Much appreciated. And in due course, there are further ARPAS-UK CPD and future-facing sessions, which can be found on the ARPAS-UK CPD page, which is www.arpas.uk/CPD. Let's keep it simple after all. And we have two coming up fairly shortly on more on the ecological, environmental side of things. On, she says, get it to the correct page. Come on. Here we go. On integration of UAVs and remote sensing into ecological consultancy, and distant clouds, drone flying on a remote UK overseas territory. I can tell you that that's St Helena. And then we have another one in June on UAS uses in agriculture, including spraying and spreading, with further CPD sessions, webinar sessions being planned as well. If you're interested in taking part yourselves, please do get in touch. We are always delighted to help share information amongst the drone industry and the vertical industries that obviously sort of incorporate and link in with what and where drones are used. Thank you very much again today, gentlemen, and we will hopefully see you again face to face in the future. Thank you very much indeed to everyone else as well. Bye.